Okay, now we start about graph review. Okay, because graphical algorithms are a very important part of the algorithmic study, and we'll find that many of the algorithms can be represented using graphs. So we must study the graphs before we go into more detail about the graphical algorithms. And this is a nice place to review that. And the more details about the graphs can be found in the Corman book, the algorithm book, in the appendix B. Okay, so there are graphs and trees and the properties of those data structures, which are very important to many algorithms. Okay, so let's start with the digraph. So digraph is nothing but a directed graph. Okay, what is a directed graph? A graph where there are edges which are directed from one vertex to the other vertex. Like suppose digraph is a G, which is V comma E. V comma E is V is a set of vertices and E is the set of edges. You can see here that E is a subset of V cross V. That means because edge is connecting a pair of vertices, so this means that E will be a subset of V cross V, because the graph can have all pair of vertices connected, can have a subset of vertices connected. Okay, so we're now after the directed graph is like this. Okay, so this is A, B, and C. So this is a directed graph. Okay, so A to B, C to B, and then A to C, C to B, and then A to B. So this is a directed graph. If we can represent them as nodes, so then there will be direction between the edges. So you can see that A to C is not same as C to A. Okay, because the direction is important. Now you see the undirected graph. This is just opposite to the directed graph, where the direction between the pair of vertices is not that important. Okay, so E contains undirected pairs. Okay, undirected pairs means like this vertex pair, connecting vertex pair, but there is no direction. So what about the E size of the set of E? So mod E is NC2. You pick any two vertex and make a connection between them. How many such vertices connections are possible? That is order of mod V square. Here mod V means the size of the vertex V. So here, so NC2 becomes order of V square, because NC2 is like n factorial and then 2 factorial and then n minus 2 factorial. Okay, so this n factorial can be represented like n times n minus 1 times n minus 2 factorial, and then this 2 will be cancelled. So this is actually n into n minus 1 by 2, which is like n squared. Like here it's for graphs, this is V squared input size. So now if we take log in both sides, so log E will be log V, like 2 log V. So the if you take asymptotic analysis and consume the constants and lower order terms, so that will be order of log V. Now what about the if it's a connected graph? So connected graph means from one vertex you can reach, from one vertex you can reach to any other vertex. So then it's a connected graph. If it's a disconnected graph, there is two separate sets. They will have no edge between them. So from one set, you might reach in that set from one vertex to another, but in the other set, which is disconnected, you cannot reach from here to there. Okay, because there is no edge between them. So if it's a connected graph, then mod E is greater than, so the minimum size of mod E is V minus 1. So let me show you with an example. Like suppose this is a connected graph, so that this, and this. Okay, so you can reach from here to there, there to there, and there to there, and then from any vertex to any vertex is reachable. But this edge is not connected, or this edge is not connected, or this edge is not connected. Still the remaining is a connected graph. And so the minimum number of edges with 4 vertices is 1, 2, 3. 3 edges. Okay, so that is vertex minus 1. So that's why mod E greater than mod V minus 1 for a connected graph. And so if you take log in both sides, in this case also, you will see that the minimum bound is also omega of log V. Now if you combine this two, log E is big O of log V and log E is also omega of log V. So together log E is theta of log V. Okay, so that means in connected graph, edges and vertices are polynomially related, and so their logs are comparable. Okay, so their logs are comparable, polynomially related. So now once we have talked about the digraphs and the undirected graphs and the relation between their vertices and edges, so let's talk about the graph representation. When we try to represent a graph in a computer program, because we have to finally program our algorithms, so how we do that? We have two different representation. Okay, one is called adjacency matrix representation and the other is called adjacency list representation. So what is the adjacency matrix representation? Adjacency matrix of a graph G with a set of vertices and a set of edges, where V is 1, 2, up to n number of vertices, is the n cross n matrix. Okay, it's the n cross n matrix. So it's the vertex number n. So it's the n cross n matrix. Like suppose this graph 1, 2, 3, 4, 4 vertices. So it's a 4 cross 4 matrix. And what it says is a matrix A given by Aij, where the element given by the row and column given by the coordinates of this matrix will be 1 if between I and j there is an edge, and will be 0 if between I and j there is no edge. Okay, that's called an adjacency matrix representation. Suppose in this digraph between 1 to 2 there is an edge. So in row 1 column 2, you see here this is a 1, that means they have an edge, but 2 to 1 there is no edge. So row 2 column 1 there is no edge. Okay, 0. So now 2 to 3 there is an edge. So 2 to 3 row 2 column 3, you see there is an edge, but 3 to 2 there is nothing. So 3 row 3 column 2 there is no edge. Similarly 3 to 4 there is no edge. 3 to anybody there is no edge actually, so this is entirely 0. And 4 to 3 there is an edge, so row 4 column 3 there is an edge. Okay, so this is the way of representing adjacency matrix. You can very well see that this is not a very good way of representing when the graph is a sparse graph. If they have edges between, it's completely connected between every pair of vertices, then this is a good representation. But those kind of graphs are rare which are completely connected. Otherwise, this is taking a theta v square storage, because this side is v, this side is also v. Now, we do not really talk about storage when talking about algorithms nowadays, because the storage is so cheap now. It doesn't really matter, doesn't really affect the performance in that way. But the square storage for a graph where only probably few rows, few positions will be used and rest will be 0, it's a really waste of space. So the scientists thought about how to do some better representation of graphs instead of going for a theta v square storage. So this is not good for sparse graphs. Not good for sparse graph. Okay, if it's a dense graph, that means they have more edges, then this is a better representation. But for sparse graph, it's just an absolute no. So then what we can do? We can use adjacency list representation. What is adjacency list representation? Of a given vertex V belonging to A. So it's a adjacency matrix representation is mostly for a whole graph. Adjacency list representation is vertex by vertex. Okay, so for a given vertex V belonging to A is the list adjacency V of vertices adjacent to V. Okay, so adjacency is a relation between two vertices. Like this edge is adjacent to vertex A and B. We say like that. And incidence is a relation like this edge is incident on the vertex A because it starts from there. So adjacency is a relation between two vertices, and incidence is a relation between a vertex and an edge. Okay, relation. This is a relation or relation between a vertex and an edge. So adjacency of a vertex V is degree of V for an undirected graph, and just the out degree of V for a directed graph. What is a degree and what is a out degree? Degree is actually the number of edges incident on a vertex is the degree. So like suppose this is a graph. So here suppose this is the undirected graph. Now the degree of this vertex, this 1, 2, 3 and 4, degree of this vertex is 1 and 2. So there are two edges coming out of it. So for 2 the degree is 1, 2 and 3. 3 edges coming out of it. Okay. Similarly for 3 the degree is 2, and for 4 the degree is again 3. So but if it's a directed graph, immediately we just consider the vertices, the edges going out of the vertex, okay, not all of them. So we do not consider all of them. So if this is a digraph, then we just consider like degree of 1, the out degree we'll say, not the in degree. Out degree is the number of vertices going out of that, like for 1, out degree is 1. You see one edge going out of 1 and going towards 2. And the in degree is just the vertex, the edge coming into that vertex. Okay, so for 2, in degree is 1 and 2, and out degree is 1, that edge 2 to 4, which is going towards 4. For vertex 4, the out degree is this and this 2, and in degree is 1, in that way. Okay, so out degree is the now edges which are going out of a vertex, and in degree are the edges which are coming inside. So for adjacency of a vertex, we will say the degree when this is an undirected graph. Degree of that vertex, adjacency of a vertex is degree of that vertex if it's undirected graph, and adjacency of a vertex is out degree of that vertex if it's a directed graph. Now consider this example. Okay, what is the adjacency of 1? Because this is a directed graph, we just consider out degree. So adjacency of 1 is this edge and this edge, 1 to 2 and 1 to 3. You see adjacency is 2 and 3 we write. Okay, degree of vertices is this is actually 2. So this one and this one, 2 and 2, 2, 2 and 2, 3. So these are this is the 2. Adjacency of 1 is 2. Adjacency of 2 is 1. That is going to 3. There's 1 out degree. Adjacency of 3 is a null set because there is nothing going out of 3. And adjacency of 4 is 3 because there is one edge going out of 4 and towards 3. So that's why we write 3. So it does not mean that it's a count. It means that 2 edges going out of 1. One edge going out of 2 towards 3. One edge going out of 4 towards 3. So you see this representation does not waste any space. It just writes the number of edges outgoing. That means the out degree for a digraph and degree for an undirected graph. Okay, so these are the two representation of graphs. The first one is the adjacency matrix representation of a graph and the adjacency list representation of a graph. For the adjacency list representation, we just go vertex by vertex and see what are the edges coming out of it for a digraph and what are the edges incident on it for a the undirected graph, which is called degree also. Now this representation is a good representation for both a sparse and a dense graph, but for a very dense graph it's better to go by this one. But if it's a very sparse graph or a generally sparse graph, it will save a lot of space if we go for adjacency list representation. Now you see there is another thing which is called handshaking lemma. Okay, so here handshaking lemma says that if there is all the students in the class and everybody shakes hands with everybody else, then the number of handshakes in the whole class, total number of handshakes, will be even. Okay, what does it mean? It's how it says, it's a sum of degree of every vertex is 2 times the edge set, okay, size of the edge set, where small v, every small v belongs to capital V. So number of hands shaken is always even. Why? You think about it. If there is a handshake, then both the vertices are, both the end point, both the persons doing the handshake are counting it as 1 and 1. So similarly, if I add an edge to a graph, so the edge is between a pair of vertices. We already said the edge is connecting a pair of vertices. So both the vertices degree will be increased by 1. This is for the undirected graph. Please remember. So it's not an in degree and out degree. It's just the degree. So when I add an edge between a pair of vertex, for both sides, their degree will be increased by 1. So it is always, a factor of 2. So it's always an even number. So every time we put an edge, we add 1 to both the end vertices. Actually, end vertices means the degrees of end vertices. Now, in general, so handshaking lemma is very important. Okay, always remember the sum of degrees of the total for all the vertices in the graph is always even. Okay, so now one more time we talk about these things, this adjacency list and stuff. For undirected graph, adjacency list representation uses theta of v plus e storage. Okay, so this one you can easily see from here that this is the v and these are the edges coming out of it. So this is v plus e for all the vertices will write 1 2 3 4. So that's a v set of vertices and then every edge coming out of it. So that is v plus e storage, and it is a sparse representation because if you sum those edges to 3, so if you sum those edges, they will actually become all these edges. So it's all the vertices we write and then all the edges we write. So it is a sparse representation, often better than adjacency matrix. I already said that. Now you should also remember and try to study what is a tree. Okay, a tree is a cyclic graph. Okay, a tree, if in a graph, suppose this is a graph and this is a graph. Okay, and suppose you write like this, and if you do this, then this is a graph, but this is not a tree anymore because there is a cycle in that. So, okay, you can go back from the starting point and then travel around and again come back to the starting point. Okay, so this can be a tree, but if I connect this edge with a direction like that, it will not be a tree. Okay, undirected graph is also possible, and so the definition of trees are important. What are simple trees? These are also important. So please read the appendix B and try to understand more about this concept of digraph, undirected graph, connected graph, and there, the polynomial connectivity between the edges and vertices set, the representation of graph using adjacency matrix, adjacency list, and the handshaking lemma, as well as the trees. This will prepare you more for the next few topics, which will be about graph algorithms, and you'll feel more comfortable about that. Thank you.